Thank you, John, for the invitation and for hosting me. It's a real honor to come here and to present this work to you. As John said, my background is in engineering control theory. But from the beginning, even when I was starting my PhD, I've been working on safety critical control systems and really trying to think about how to automate some or a lot of what is done today manually in these systems. And so that's been, I think I'll start with a little bit of that motivation. But the theme of the talk is kind of robotic systems, so automation. And coming from a control, a model-based perspective, we know that there are things that we can model really well, but we know that there are things in the system, namely the big things like environments that we might not necessarily be able to model ahead of time, but that we could potentially learn. And so I've been very interested since moving back to Berkeley in how one might take a safety critical control structure and integrate learning in a way where you can still make some assessments or some guarantees about the behavior of the system. And so that's going to be kind of a theme that will follow through the talk. So I'm going to start with some motivation and motivating examples, and then go through the safety critical control structure and some examples of that. And then in the latter part of the talk, I'll introduce how we've been, maybe the first steps of how we've been incorporating some learning algorithms into this safety critical control structure. So hence the term safe learning. Okay, so this is an application, as I said, I've been working on for maybe like 25 years now. This is a project that we've been doing with NASA and the FAA. These are just some snapshots. This is from a while ago, but the Oakland Center is one of the air traffic control centers around where I live. So it controls most of Northern California and actually a lot of the Pacific Ocean. Controllers are basically, each controller is responsible for a sector of airspace. They get the flight plans ahead of time from aircraft filing their flight plans with the FAA, comes to the controller. They know ahead of time the rough trajectory and when the aircraft will come into their sector, and they're responsible talking to pilots over radio channels, guiding that aircraft from its entry point into their sector of airspace to its exit point. And typically, you know, they have a rough guideline, but that doesn't include collision avoidance. So one of the key tasks of air traffic controllers is to make sure the aircraft stays separated from each other. And that's a kind of, you know, very safety critical system. The aircraft typically in a space like this, if you're away from the airports, there has to be about a 5 lateral mile separation between aircraft, 1,000-foot vertical separation. Okay, so this slide just shows a little bit of the structure. In terms of the merging traffic, you can see that's the Bay Area. These are actually aircraft coming into San Francisco, and we're just plotting their points over time for a few hours. And you see this kind of structure of routes. So there's a bit of a structure of highways in the sky. They use beacons on the ground to indicate waypoints, and then aircraft will update as they fly using their inertial measurement units as they fly over these waypoints. GPS is now used, but it's not a system that relies on GPS, interestingly, because of the possibilities of hacking and losing GPS. So even that, you know, that's been taking a long time to get certified for use in different aspects of air traffic control. Okay, so the high-level cross-traffic, you know, aircraft that are flying at the high level, not coming into the San Francisco airport, and then kind of the structure of merging traffic. And those kind of pink regions, those are sectors. So each sector is controlled by a single air traffic controller. So main goal of controller is to keep the aircraft separated. And we've done a lot of work in sitting behind air traffic controllers, watching what they do, basically looking at how they maneuver aircraft through this system, and observing their behavior. So what would an air traffic controller do if aircraft are in danger of losing separation with each other? And so over time and collecting a lot of data and watching air traffic controllers, we've built up a model of an aircraft in an air traffic control system in terms of kind of the control modes. So it looks like a finite state machine with transitions. Each of those states, though, represents the physical dynamics of an aircraft under that particular control law. So most of the time, the aircraft are in that center mode. They're flying at their average speed, which is optimal for the altitude they're flying at. And, you know, maybe in some cases, in this stylized case that I've shown here, the air traffic controller can speed up or slow down those aircraft a little bit. So min speed, max speed, only by a little bit, because they won't change the velocity. It's optimized for the altitude. And they typically don't change the altitude if they don't have to, unless the aircraft is already changing altitude. And, you know, if that doesn't work, they'll go into a detour, you know, cut shorter route, or they'll actually vector the aircraft away from its route to stretch the path length. So, you know, very simple maneuvers that are kind of, you know, simple to describe to pilots and fairly simple to understand. But it's interesting when you look at air traffic controllers, what they tend to do is they'll look at the set of aircraft in their sector and they'll group together aircraft kind of cognitively into different groups of aircraft, so the most safety critical. So the two aircraft that are coming close to losing separation would be the ones that would be the most critical to control. You know, there's two other aircraft that are maybe approaching that. But air traffic controllers tend to line aircraft up on a single route, flying at the same velocity, because then it's a fairly simple problem. You've got basically a bunch of aircraft that are acting like one aircraft. And so it's a simple sort of way to monitor movable data like aircraft. Okay, so they, and also controllers tend to, they tend to sort of judge themselves or their abilities by the number of times they have to vector, the number of times they have to touch an individual aircraft and take it off its desired route. So it's kind of good to, they like to minimize the number of times they have to maneuver an aircraft or the number of aircraft they have to maneuver away from the nominal. Okay, so that's just setting the stage, and that's a problem, as I said, we've been working on for about 25 years in terms of understanding what kinds of functionality one could automate and how one could design automation that would actually help air traffic controllers when you have a human in the loop. So I'll show some examples from that work. But over the past 10 years, this field, the field of air traffic control, which is a slow-moving conservative field, is changing because there's a lot of pressure on the FAA from large businesses to allow them to fly other things through the airspace. So these unmanned air vehicles from Google and Amazon are just one example. They would like to be able to fly their vehicles, of course not at the same altitudes as commercial aircraft, but you know, in cities and urban areas, typically you've got controlled airspace around airports, and that's, you know, the whole of the city. So you want to be able to make sure that if you have UAVs, you know, they're not going to be intersecting the paths of the aircraft. So we're working on a project with NASA, and we have been for the past few years on designing an unmanned air system traffic, UAV, unmanned aerial vehicle traffic management system, and the acronym they use is UTM for that instead of ATM. And so it's sort of interesting because in contrast to air traffic control, where there's a big legacy system that, you know, as you're introducing automation, you have to work with the system at hand and think about how to update it and what functionalities to automate. Here it's a bit of a clean slate. I mean, in fact, a lot of the airspace we could segregate, and then they're asking, what are the structures? What kinds of structures from air traffic control might we want to adopt, or should we just do a complete new redesign? And so that's kind of represented here in terms of these stylized diagrams that, you know, still there will be a human or a number of humans in the loop. So there's probably some of that structure which is designed to help people understand how the system works, if they're, you know, a human in the loop controlling it, that you want to maintain and you want to adopt. And so I'll show some examples from our work there. But this, as they are UAVs, they're much more autonomous. I mean, there's not a pilot inside. And so at least for tactical collision avoidance, that's something that you would want to do automatically here. So that is not done by a human, that would be done by the autopilots on board. So there has to be an ability to sense in some way and avoid other aircraft, and that has to be done on board. So that's a project that we're working on. And then just sort of continuing maybe to another extreme, and I think this is where, you know, like all the new startups and things like that are happening, in particular, those in autonomous driving. These are just two companies in the Bay Area that, you know, my students are going to be interning at this summer. One is a Skydio. This is the company I was telling you about, Amir. This is a flying camera. So it's basically a quadrotor with a bunch of cameras on. And it's kind of designed, I think, for people who want to have a continuous recording of their sport life. So that instead of having a selfie stick, you'll actually have a selfie UAV that will take your pictures. It's turning out that it's big in China. There's a lot of apps which people are, that can sort of take images and do a lot of signal processing around those images of yourself. And so the idea is to replace a selfie stick with like a continuous flying camera. Neuro is a autonomous vehicle, but there's no people inside. It's a delivery vehicle, and it's just starting its field testing. So now these are the different challenges than in air, because there's a lot more. Air is free. Well, not completely free, but there's a lot more. There's many more things in the environment that happen when you're close to the ground, close to people, or on the ground driving around. Okay, so as I said, I'm going to talk about, the first part of the talk is about safety critical control. I'm going to talk about a tool that we've been developing for about 20 years and the different aspects we've been doing. So that's a reachable set. It's a method of model checking for control systems or for hybrid systems. And then for the latter part of the talk, I'll discuss how we integrate learning into this control structure. Hybrid is, we're using that in the sense of a combination of discrete state and continuous state dynamics. So thinking back to that finite state machine that I showed representing an aircraft under air traffic control, different finite states representing the control mode of each aircraft, but within each of these states, there's the physical dynamics representing the evolution, how the aircraft is flying under that discrete control law. So it's really a blending of, it's like a finite automaton where each state of the automaton represents a continuous control system. Okay, so first part of the talk, so the concept of reachability. So let's present this from a safety critical point of view, because that's kind of the world that I've been living in. Suppose you had, and let's just focus on a continuous system for now. This is, it's not really system specific, but a lot of the computations we've been doing have been focused on differential equation models of systems. So this is describing the physical dynamics of an aircraft flying through under a particular set of control laws with a particular set of disturbances, things that you can't model but you have to protect against, like actions of another aircraft or wind in the system. So that kind of, moving towards, say, an environment where you don't know anything about, or you don't know much about the environment. All right, so state X could represent, positions and velocities of a vehicle. U inputs actuation capabilities that either the pilot or the autopilot, you as the designer of the automation, have control of. And D, disturbances, things that you can't model, but we're going to assume that they're bounded. We don't know what they are, but we assume that we know the range or the space in which those disturbances lie. And the idea of a backwards reachable set is the following. So suppose you could characterize, let's talk about unsafety. I use red to represent unsafe sets. Suppose you could characterize an unsafe configuration as a subset of the state space of the system. So the board or the screen is representing the state space, X lies in the state space. G at time 0 is the unsafe condition. That means, say, in your set of 12 aircraft in a sector, any pair of aircraft is losing separation with each other. Okay, so I can characterize that as a subspace in the relative dynamics of that group of aircraft. So assuming that I can characterize unsafety as a set of conditions in the state space, then the backwards reachable set is the set of states for which, for all possible control inputs, things that you as the designer can affect, there exists a disturbance which, under the dynamics of the system, could push the system into that unsafe region. It doesn't have to, but it could. So there's uncertainty in the disturbance. So we're conservative on the side of the disturbance. So it's like a game. We're pitting control against disturbance, and we're asking what are the set of states for which you could become unsafe under the dynamics of the system. And if you know the model, and even if you know the model up to some uncertainty, you can compute the set of states. I've shown it here in this kind of pink region. Indexed by time, G of t, is that set of states for which, for all possible control, a disturbance could push the system into the unsafe region in at most t time units. And typically we compute backwards reachable sets. So we look at the set that we want to or we don't want to reach, and then we compute the configurations that could get there under the dynamics of the system. So that's kind of the key idea. And this is not invented by us. This is an idea of reachability that's been kind of it's sort of a fundamental idea in control. But the key, as is everything, is in being able to compute these sets. And so that's where we've made some contribution. Let me just say a few words about that. The actual set itself, and I'm just going to have a sort of slight animation here, it's computed iteratively by solving a particular partial differential equation. So it's, as I said before, we use game theory to solve this. And so we draw on tools from optimal control and differential games. And we solve a particular differential game problem where instead of computing the set directly, what we compute is a function, which is a value. That value function represents at any state x at time t, future cost or reward that would be incurred by the system if you start at state x at time t and you evolve. And that reward is going to be, the cost will be high if you enter the unsafe set, and it will be low if you avoid the set. Okay, so that's kind of a structure that I think many people are familiar with, representing the value based on the kind of cost or benefit that you would incur. And so this function jx of t is our value function, and we showed this is a variation on a very traditional what's called a Hamilton-Jacobi-Isaacs equation for computing reachable sets for safety systems. So there's a particular min with 0 that freezes states. Once a state goes through that unsafe region, we want to label that as unsafe, even if it ends up outside, over the time horizon. Okay, that function, so we evolve the function, but we want to record the sets itself. Well, the zero level set, the sub-zero level sets of that function that we're computing represent that backwards reachable set. So it's actually, it's a nice mathematical structure, because what you're doing is you're evolving and you're manipulating a function, and then you're recording the set as implicitly through that function as the zero sub-level sets of that. The advantage of that is that you can represent, disconnected sets. You may have, disconnected sets. You can represent that with one function, evolve the function under the dynamics, and you'll get the evolution of the individual sets. Of course, the disadvantage is the curse of dimensionality, which it's a Bellman operator that we're propagating here. Basically what we're doing is value iteration in continuous time, continuous space. And so the more dimensions we have in the continuous state space, the harder computationally this problem is. It's an exponential computation, because you're basically gridding up the state space, and you're computing the solution on each grid point. Okay, so this just shows, starting out with some function, we're looking at a slice of that function. We're taking, we're recording the zero sublevel sets as the unsafe region. Okay, but just a few properties. If the set is controlled invariant, that means that if after some time that set converges, it doesn't grow anymore, then you have the property, which is an interesting property, it needs to be proven, that any super zero level set is also invariant. So what that means, invariant means that if you are outside of that set, there exists a control law which will guarantee that you stay outside of that set. That's a property of being in the blue region. And so what we're saying here is that you can also prove that you don't reach a set by proving that you don't reach an over-approximation of that set. But the invariance property is propagated to the over-approximations, and that can be represented as a one-level set or a two-level set, a super zero-level set of that function. The other interesting thing is that the more you know about the system, so in our case, what we don't know about the system, we're lumping into this disturbance function. The more you know about the disturbance, the less conservative it becomes. So in our case, conservatism, it's an unsafe set. So conservatism would be, you don't know, if say you don't know very much about the disturbance, then your unsafe set is going to grow. The more you know about that disturbance, in fact, if you could characterize it perfectly, you'll minimize the size of that set. There's probably still going to be some set because you're subject to the dynamics. I mean, you just can't turn fast enough to avoid something. So that's something that we're going to come back to a little bit later when we talk about how we might use machine learning to learn those disturbance functions better and make these sets less conservative. So really starting to think about using these sets as a bookkeeping mechanism for safety, recording the information that you know and using it to compute a value function. Okay, so numerical computation. So this is actually Ian Mitchell, who's a professor in CS at UBC, was my first PhD student when I was a professor at Stanford. And we worked on this problem together, and then when he moved to UBC, he encoded these computations in what we call the level set toolbox for reachability. This is the link to it. Ian is wonderful at documenting everything and providing well-documented examples. So you can go to this site, you can download the toolbox, you can run some of the examples, you can pull out his examples and put in your own dynamics and run it and get these computations. So it's, I mean, we were part of the development, but I think, you know, just sort of from it's a system that's fairly easy to use. We use it in the course I teach. And since then, we've been developing a number of wrappers to go around this, a number of tools, which I'll spend a few minutes talking about. Okay, and this just shows, you know, you can get these, you know, funky looking, generally non-convex, even disconnected sets, because you're basically just representing them implicitly through a value function. And also, interestingly, for control, it's nice because the value j, you know, you can encode. There's many different functions j you could use and you could propagate. But one popular one to use is a distance function, a signed distance function. So, you know, whether you're inside the set or outside the set, you just look at your state, you evaluate your j. It not only tells you whether you're inside the set or outside of the set, but it tells you something about the distance to the set. And that's maintained as you do this computation. That's a useful information for control. Not only am I safe, but, you know, how far am I away from that boundary is something that you can easily pull out of this computation. Okay, so this is a first example. This was actually back at Stanford. This when Steve Wasslander was a student with me. He's one of the 4 students sitting there. So this was back before you could buy a quadrotor at every street corner. These are ones that we constructed and built ourselves with carbon fiber tubing, 2 PCs on board. But there are 4 quadrotors. There are 4 students. Each student is joysticking a quadrotor around. So the data is being played back on the right. And what you see around each quadrotor are 3 sets. Those are the relative reachable sets from each quadrotor with respect to each of the other 3. So when one quadrotor gets to the boundary of the reachable set of another, that other quadrotor executes an avoidance maneuver. So the automation on board the quadrotor takes over, the student no longer has control, automatically, and it guides the aircraft away from each other according to the optimal control law that came out of that Hamilton-Jacobi computation. So you not only get the set, you get the control law that keeps you on the boundary or pushes you away from the boundary. Now this is kind of a special case. These dynamics are such that this is a very high, I mean, it's a 4-dimensional model that we're using, but there's 4 aircraft, so a 16-dimensional system. That's pretty high for our computation. This is a special case where you can decouple this into 4 4D computations that you can run in parallel. And that's not always the case. I'm going to say a few words about that later. But that's why we could do these computations in real time and run the thing in real time. But that requires a proof. Just to say one word, we've gone through, conceptualization, running it on our simulation, running it on our kind of university test beds. But we were part of a DARPA program. This was about 12 years ago that we did this experiment at Edwards Air Force Base in California, where we had, so Boeing was part of the DARPA program too, but there's a Boeing F-15. They're both piloted aircraft, a T-33 test aircraft. And the T-33 was running the code of the collision avoidance. So it had our algorithm connected to the autopilot. And when they were doing the sorties, the T-33 pilot was hands off. So the algorithm was running the sortie. And so you might have seen just in the first part of that experiment that we've got the boundary of the reachable set around one aircraft. And when the T-33, or when the F-15 moves, it sort of blunders into the path of the T-33. As soon as the T-33 touches the boundary of that reachable set, it executes an avoid maneuver. And you start seeing the avoid maneuver here. So it was nice to run this and actually have it working in real aircraft. Okay, so you can turn this computation around. It's not only for avoiding sets. You can capture, so you can reach a target set. So now the problem is turned around. You want to compute the set of states which will reach a target set despite the worst possible disturbance. So basically what was a max-min is now a min-max in that Hamilton-Jacobi equation, but it's the same computation. So it's a capture set. And you can sequence these. So for hybrid systems, we're switching between different dynamics, switching through an automaton that has these different continuous dynamics. So you can do a kind of a chaining. You can capture, compute the basin from which you'll get into the basin of the next mode to get eventually to a desired target set, while avoiding an unsafe set at the same time. So this is what we call the reach avoid operator, the set of states from which you can reach a desired configuration, even through mode switching, while avoiding an unsafe configuration. And because you're doing the manipulation on functions, that kind of, the constraint that you avoid an unsafe set, it's like a simple masking of those functions. So that's a nice, working in functions instead of sets is a nice way to be able to do this manipulation eventually of these sets. Okay, so let me say a few words about what I said earlier. So this is a computation that's, we have 4 dimensions, 4 continuous dimensions is something that we can do in kind of real time. It depends what you mean by real time. But 5, 6, that's, by the time you get to 6 or 7 dimensions, these, to do kind of a realistic set, like a nicely, capturing the kind of dynamics that you saw in some of those examples, it can take about a day to compute. And often you run out of storage on the kind of computer you're working in. So it's just the dimensionality problem and the ability, the fact that you're computing the solution over a state space, so you're computing a value at every state and you're iterating that. So this is a problem that there's a community of people working in reachability, and so there have been different methods to use, and we've got some characterizations there, and I'm just going to mention a few that we've worked on, but others in the community. So approximations. If those dynamics are linear, and if the sets are, like can be represented with, a sort of quadratic representation, then the problem turns into a linear quadratic problem, and there's some analytic computation that you can use. So you can simplify the problem. You can over-approximate sets. You can over-approximate dynamics to go to higher dimensions. And so that's been a direction that we and others have taken. You can impose practical constraints on the problem. That's often what we do from an engineering viewpoint, and I'll say a few words about that for the UTM problem. And some interesting things in mathematical structure and decomposition that I'll say a few words at. So trying to really, like from an engineering standpoint, how do we make these computations feasible for realistic systems? Okay, so in terms of an approximation which is imposing practical constraints on the problem. So this is an example which comes from, as I said, this UAV traffic management. And the idea is to take advantage of structure in the airspace. So the fact that you probably don't want UAVs flying everywhere. You'd like to have some sort of corridors, which are popular corridors to fly. And safety critical for UAVs, because there's no pilot or passengers in it, means that you don't want it to hit anything else, or you don't want it to fall and hit something on the ground. And so this is just a snapshot. This is part of the project that we've been working on for NASA. But we just used a fast marching method to compute shortest paths, where shortest means lowest cost, and low cost, it's cheaper to fly over water, it's cheaper to fly over sparsely populated areas. It's very expensive to fly around airports, that's San Francisco and Oakland airport airspace, and pretty expensive to fly over heavily populated cities. And so that's a very fast, you can do this computation, you can recompute that online, and this just shows paths from it's an Amazon warehouse in Concord, California, coming out to some of the major Bay Area points for drop-off. So that was something that we did for NASA. But that structure, as you know, it's path planning. So you put these constraints in. What comes out is this kind of trunk routes, so highways in the sky, something that we see in the air traffic system, and then short deviations into populated areas. Okay, so that led us to think about platooning, this idea of that air traffic control follows, is sort of lining up. You've got a finite number of routes, so try to line up the aircraft in a way that each aircraft isn't looking at its constraints with respect to a bunch of aircraft, but it's basically trying to solve the collision avoidance problem with respect to the aircraft in front. So really reducing the dimensionality of the problem by imposing structure on the system. So it's a very practical way of viewing a system where we can now incorporate the constraints of reachability in a realistic, real-time way into that structure. So a platoon of UAVs, the idea is that there's a leader of a platoon, there are followers, and the followers are controlling themselves with respect to the vehicle in front. This is an idea that was proposed for it was about 20 years ago where they were looking at automating the inner lane of California's highways by having a roadside control structure that cars would lock onto, and then there would be platoons of vehicles driving fairly quickly at fairly short spacing between each other. And so we kind of copied that idea for this UAV project. So vehicles can be, so this represents, again, a UAV under that control structure. You can be a free vehicle, not in a platoon. If you join a highway, you either have to be a leader of a platoon or a follower in our platoon. And if you're a single vehicle, you're just a leader in your own platoon. Faulty, so if something goes wrong, you're only flying at one level, so you can descend to get out of the way. At least if you can descend. We have another project which we're working on with a different NASA group on how to design an emergency landing system. So if something wrong happens with a UAV, what's under maybe reduced control authority, how do we quickly compute available landing positions given the topology of the region from some database that's available in the cloud? Okay, and so here, we prescribed control laws for each of these modes, but we used reachability to automatically synthesize the guards. How do you safely transition from one mode to the other? So those transitions in this hybrid system from mode to mode are automatically synthesized by the reachability computation. And here's just some results that, again, we used 4-dimensional models for each vehicle, but we're projecting the sets down onto the 2-dimensional, the lateral position, so basically the X, Y space at the same altitude. The top row just shows a sequence at 2 time points of 2 vehicles, so a red vehicle that's joining a highway, and the heavy dashed line represents its target set. It represents the set that it's trying to reach and then we have a simple control law that will snap it onto a moving target that's moving along the highway. And the avoid set is with respect to the other aircraft. And that's in this case, there's a blue aircraft. So you see the reach and the avoid parts are separated as they're getting closer together. Similarly, on the bottom row, we see those corresponding sets for the blue aircraft. Okay, so the reach set and the avoid set. And so those, hitting the boundary of those sets indicates the transition in the indicates a guard has been triggered in that hybrid system, and a new control law will take over to get those aircraft to reach the highway. Now, in this picture, we're not showing those sets. They're computed in the background. They're there. We're just not showing it. But you can see through the sequence this kind of organic motion of aircraft forming a platoon on the highway. So the kind of merge and join, again, generated automatically through those reachability calculations. So you want to be robust to disturbances, like vehicles that are flying through that are not following the rules. And so here you have this red vehicle. It's detected, so it has to be detected. We're assuming that we can detect these vehicles, and that as it comes closer, it's moving in a way that it's a vehicle that's an intruder. So that kind of state has to be detected. But then with the reachable sets can be computed again in real time, and the avoid operator, so you see that red region represents the avoid operator, and when each vehicle touches the boundary, they depart from the highway, go into free and non-highway mode, and then when the vehicle is passed, they get back onto the highway. So again, those are computed just based on the dynamics and the uncertainty. So that's basically the reach avoid operator in play for this UTM problem, where we assume that we can detect the state of the vehicles. And we've just got a little robotics lab where we try out a lot of these experiments, mostly to be able to test the communications. What are ways that we might provide information transfer back and forth between the vehicles. Here, the sensing is done externally, and that's a problem we're working on now. How do we now equip the vehicles with the kind of sensing they would need to be able to do this recognition and tactical collision avoidance in real time? Let me say one more word about approximations. This is an area that we've also been working on quite recently in terms of making this reachable set toolkit more amenable to high-dimensional problems. And so this work, we call it, it's called Decomposition. So the idea, and I'm going to illustrate it through kind of a couple of examples, which are not high-dimensional examples, but which serve to illustrate the point. If you had, say, in this case, a four-dimensional, this is a four-dimensional planar vehicle moving, and its states are x, y, v, and angle. Okay, so it's got acceleration. It's an acceleration-controlled vehicle. You could take that four-dimensional set and you could decompose it into two three-dimensional sets where there's overlapping. So an x, y, v set and an x, y, phi set. And then do the computations in parallel for those two sets using the missing state variable as a disturbance. So we're missing that variable in one of the lower dimensional computation. We're just going to treat it as a disturbance because we have a technology for incorporating disturbances. And so in a number of problems, you can do that decomposed. We call it decoupling disturbances. You can do that decomposed computation using approximation in terms of that disturbance model. And so what we're showing here in green is the actual four-dimensional set projected down into two three-dimensional projections. And then in gray is the over-approximation of that set computed quickly through the two three-dimensional computations. And you can, because of the disturbance, the way we model the disturbances, you can guarantee that it's an over-approximation of the set. We took that idea and we asked, could we actually use that in a way to do exact computations? And so this is sort of more recent work, and I'm going to use this 3D system as more of an illustrative, the sort of Dubin's car model as an illustrative model for what we want to do. But suppose you had a system, say full dimension is 3, again, not high dimensional, but let's just use it as an illustrative example. Then, we could compute the 3D reachable set, and we do compute the 3D reachable set. But suppose that was an n-dimensional system where n is greater than 6, then we wouldn't be able to compute that in real time. But another idea coming from this, this decomposition is that suppose we decompose that three-dimensional system into two 2D subsystems, one which is x theta and one which is y theta. And so the idea is that if those subsystems are self-contained, and self-contained means that the variables that govern the evolution of those dynamics are all contained in that subsystem. So you see that, you know, in the x theta system, all you see on the right-hand side are, you know, are basically variables. So if v is fixed, you have theta and a control input u. In the y theta system, again, you just have theta and a control input u. So you can, if you knew the control input, you could completely describe the evolution of those two systems by, they don't need anything from the other system. So in that sense, they're self-contained. There is overlapping, though, between them. So some of the variables are, like theta is shared between and u is shared between the two subsystems. That's okay. So you could do then the two-dimensional reachable set computations, which is a lot faster than doing one three-dimensional set computation. You can do those in parallel. And then the idea is to figure out how to stitch those two computations together to compute an exact representation of the three-dimensional system. Okay, so let me illustrate again with that example, maybe just what I've said in pictures. So suppose that the actual avoid set could be represented as the back propagation of, or say the back projection of two-dimensional regions. So what I mean by that is here's a set in 3 dimensions, x, y, and theta. But it's actually if we think about these two regions that I'm showing, one in green and one in purple, those represent two-dimensional regions. And if I back project them, I can actually get an exact representation of the unsafe set, the thing that I don't want to hit. So suppose you had that property. Then, under certain conditions, you could go down into the individual two-dimensional subspaces and compute the reachable set in the two-dimensional subspaces and record the back projection to reconstruct the three-dimensional set. So here's a representation of that, of the exact system decomposition, what we've just shown. And then this is, the blue set is just comparing that by doing the direct computation of the three-dimensional set. So what you can prove is that in certain conditions, you can compute that three-dimensional set exactly by performing this projection of the target set or the avoid set, do the computation in the two-dimensional spaces, back project, and look at the intersection. And it's surprisingly, so there's variables at the intersection, but it's, what we found, there's a surprisingly large number of examples for which this works, especially kind of mechanical robotic systems where you kind of this integrator structure and you've got sort of different dependencies, but there's like chains of integrators. And of course, it's nice because the complexity is decreased. Even, you know, being able, in this case, to go from 3 to 2 is, you know, it's something that's not a big deal. But what is a big deal is now, so here's a 6-dimensional system. This is a model that we've used for kind of aerobatic maneuvers for quadrotors. And we can decompose that into 2 4-dimensional subsystems, self-contained subsystems. And then we have another, I'm not going to present this other method that we use, which is using an implicit integrator system, which allows us to eventually just decompose that down to 2 two-dimensional systems. And so that computation, you know, now we've been able to compute that 6-dimensional set exactly, just looking at the set itself and sort of interpreting the set is challenging. What we typically do is we look down into sort of projections, what projections of that set look like into interesting subdimensions. Yeah.
Possibly the intrinsic dimensionality of the system is just lower than what you get when you do the full parameterization?
Yeah, so in some cases, yes. But in other cases, there's, I mean, when you say intrinsic dimensionality, that has different interpretations. But that's not actually what's happening here, because all 6 of those dimensions are important in computing what the reachable set looks like. It's the coupling between them and how we're using how those variables that couple between subsystems interact. And that's something we don't understand. We know when it works, and we've come up with conditions on when it works. For example, if you're trying to avoid intersections of back propagations, then this computation works. So you have to have some conditions on that set that you're trying to avoid in the first place, that you can actually represent it as the intersection of back propagations. And if you're trying to avoid problem, then this works, as long as you can do that decomposition into subsystems. But how to do that? So there's all sorts of interesting questions which come up from looking at the Jordan form. Say you linearize the system and you look at its Jordan subsystems. How does that, can that guide you in terms of thinking about the structure? But it inherently is that there is some loose decouplability between some of the components of the system. But typically the system is, all dimensions of the system can be interesting and can have interesting dynamics. This is a 10-dimensional, okay, so it just shows how you sort of have to project that and look at slices of the set to see, what this means. Here's a near hover quadrotor, which is a 10-dimensional system. This one is a little bit, it's actually very easily decouplable. It's not such an interesting self-contained subsystem system. But again, we've been looking at the computation of these sets and their projections and using this now in terms of our envelopes for safety. Okay, I think I'm going to skip this next little bit just to show you in the last few minutes of the talk the results of incorporating now machine learning into these reachable set calculations. So we've talked about, given a model, even if we have disturbances, we can compute these sets for which, if you trust your models, you have a guarantee about how the set operates with respect to these sets and what control to use as you get to the boundary of these sets. These next few slides are just showing how we've been using this in real-time planning lately, and I'm just going to skip over those to get to the last part of the talk, which is on learning dynamic behavior safely. Okay. Okay, so the first foray into this was sort of a kind of simplistic point of view. Suppose you had a nominal model of a system. Nominal means that it's subject to some error. Your error was contained within the disturbances. Again, you're lumping the unknowns of the system into, in the case of differential equations, they're basically functions on the vector field of the differential equation where we don't know what those functions are, but we assume we know bounds. Conservative bounds on those functions. So what we did first was, let's first compute an envelope, a safe reachable set, based on the nominal model with these worst case disturbances. Then, when we're operating inside the safe region, let's collect data. And as we collect data, we can update that disturbance function. But as long as we're operating in the safe region with respect to the nominal model, and as long as the disturbance, the information about the functions that we don't know, as long as as we approximate that disturbance function better, as long as it stays within the bounds that we had a priori set on the system, then we have a guarantee of safety. So we optimize, we compute a better model for control within an a priori safe region. And so let me just show you these last few results through some experiments. This is the Quadrotor in the lab, and it's being asked to follow a simple step trajectory, up and down, and that's its performance goal, trying to reach, trying to track that up and down trajectory. What we did was we computed a reachable set. So here it's staying inside an envelope. Safety means it's not going to hit the ceiling or the floor. So the envelope is basically the safe region is inside some region in position and velocity space for the vertical motion of the aircraft. And that's something that we compute ahead of time with a model. And then we took the model away from the vehicle. So we asked it to learn a control law, which meant learning its own model. Again, a little bit of an artificial experiment, but just to illustrate this point, while we allowed it to keep its envelope. So it means it knows its envelope, and it knows what control law to apply at the boundary of that envelope. But if it's operating inside the envelope, it doesn't know what to do, because it starts out with no model of itself and no control law. So we start the experiment. The first thing it does is it drops to the ground, but it doesn't hit the ground. So it drops because it doesn't have a control law. It doesn't hit the ground because as it gets close, the envelope control law kicks in. And then it sort of bounces up and down a little bit. And as it bounces up, as it goes up, it learns that, oh, I applied a little bit of thrust there. And it knows it has to track that blue dash trajectory. So it knows that, okay, I can apply this thrust. And we're using a fairly simple learning scheme. This is policy gradient sine derivative. And after about a minute, it does a fairly good job of learning a control law to track that trajectory. The red, so the blue is the thing it wants to track. The red of the actual trajectory is shown in red and green, and red indicates where the safety control law kicks in. So it's not right, at the bottom, it's tempering the vertical velocity as it's getting closer down so it doesn't go through the bottom of the envelope. Okay, so if it can do that, then it's interesting to think about using those updates on the model as you're learning a better model to actually update the envelope, to be less conservative. So you start out being quite conservative, having a fairly large unsafe region that you want to stay outside. And then as you get more data and you observe how the system is operating in the environment, again, where the disturbances come in, as we've shown, as functions on the right-hand side of the differential equation for this hybrid system, you update that model of that disturbance, and then you could, once you've gained enough confidence that your model is correct, you can then recompute the envelope. And so the idea now is to try to, again, I said sort of a bookkeeping method for safety, so try to keep updating that envelope as you gain more and more information about the model. So here's pictorially, kind of going back to those images that we had at the beginning of the talk. Unsafe region, start out with some, say the smallest unsafe set for which you can certify safety. So that's based on your current model of the disturbance. And then as the system's flying, you may get something which invalidates that. So you may get, for example, a disturbance measurement which said, it's actually, the disturbance is, at this point, it's more than I thought it would be. My original unsafe set is not big enough. So using this level set function, you can expand to any super zero level set that will, and we expand to the one right, which allows you to validate the new model that you're learning for the disturbance. Okay, so it's an expansion in this case of the unsafe set. The nominal wasn't good enough. We actually have to be more conservative. We're using a Bayesian mechanism to basically evaluate the probability that there exists a level set value which validates the disturbance model. And we're typically updating the disturbance model. We do it in different ways, but in these experiments, we're using a Gaussian process to update that disturbance function over time. And the idea is that as you run this for more time, you would basically learn more about the system, and hopefully you'd be able to become less conservative in terms of the envelope. So let me show one last experiment before we conclude. I think I'll skip this one and go to, I'll show this one to conclude. Okay, so here we ran two experiments in series, and I've plotted them in parallel in this figure. So again, the Quadrotor is being asked to track this vertical trajectory. On the left-hand side, the video is where we don't include this online model validation. So we don't update the envelope based on data that we're receiving. We just use the original envelope we computed. On the right-hand side, we include the online model updates. So the right-hand side is where we're updating the envelope based on disturbances that we are recording in real time. So the thing that we changed here in this experiment is that's a big fan at the bottom of the room, and it's off right now. But halfway through the experiment, the Kene Akamatalu, who's one of my PhD students, comes and he switches on the fan, which wasn't, so the disturbance set that the Quadrotor used in its nominal model didn't incorporate this kind of big wind field that's now in the bottom part of the room. So that's a function, that's something that wasn't accounted for in the original computation of the reachable set. And so you can kind of see the difference. As it comes down, so it's measuring its state relative, and so it's measuring the disturbance because it knows part of the model. And so what happens on the right-hand side is that that safe set basically shrinks to a point at which you can validate that the disturbance that it's measuring at those states complies with the model that it has of the system. The disturbance below is giving it disturbances that will push it outside the envelope. And you probably saw it was sort of being buffeted around by the wind field at the bottom. Okay, so this is the idea, but the idea is, it's really kind of a first step, we're thinking. This is kind of a controlled scenario. Our disturbances, like the unknown structure in the system, are actually things that we can represent as disturbances on the right-hand side of a differential equation. In general, we're much more interested in environments that are more complicated, things that could be, mode switches, things that come up in the environment that you suddenly detect, that you didn't account for. So, but we're interested in kind of propagating this idea of maintaining safety with this reachable set computation and really thinking about it, as I said before, as a way to bookkeep safety and as a way to maintain a notion through this value function that you're updating or you're learning of what safety means. So then to conclude, yeah, we'll just skip that. We've been working on with Anka Dragan's group on using predictive models of people now within this context. But in the interest of time, I'll just skip that and go to the summary slide. So in summary, the idea is to focus on safety critical systems, but to understand how you might maintain as much. So there's a model that you know, and there's components that you don't know. So if you know part of the system, you should use that model in designing the control, in designing the safety critical control. But there's often things that you don't know, and so we really need to have a principled way of incorporating learning into safety critical systems. And as I said, I don't think this is a solution. I think it's maybe a first few steps towards thinking about one possible solution. And so some of the directions that we're going in now, so summary, safety, we're using a reachability analysis notion of safety. Simplicity, so again, with humans in the loop, we want to have fairly well-organized models. So a hybrid system allows you that kind of, lumping together like behaviors into modes, like we talked about for the practical examples. And now really the ability to learn from new information. So all sorts of interesting questions. If you're a safety critical scenario, you're kind of admitting that your safe sets were wrong. So how do you update? What does it mean to update them? You're backing away from formal notions of safety, and you're basically saying, yeah, well, I've collected some data that indicates that I wasn't conservative enough. It seems then you should update you should expand your unsafe set fairly quickly. But it should correspondingly take longer to be able to gain confidence that you were more conservative than you needed to be, and you should shrink it. And that learning rate, I think it's a quite interesting problem. I think it's very system dependent, but that's something that I'm very interested in exploring in different practical examples. And really, as I said, here's a method. We've got it, it's a hybrid system, but at its heart, this computation is done for each mode on differential equations where we've got disturbances coming in a fairly well-behaved way. And that's not what happens in real life. In real unstructured environments where you really want to use learning. So, I've got a picture here which I drew. This is a high level. I apologize because I'm not a computer vision person, and we've just really started working with computer vision folks on this idea of, if you do have a perception module, and you're doing a vision-based navigation task in an unstructured environment for a safety critical system, so you want to have some kind of assurances on how that system will behave, maybe it does make sense to propagate this model-based point of view. If you have a model of at least part of the system, and you usually do if you have a robot, use it. Don't take image to control, which is an end-to-end learning perspective, which a lot of folks, at least at Berkeley, have. Go image to state. So it's much easier to use the model because we know how to do state to control. That's something control theorists have been doing for decades. We're really good at it. What we're not good at is perception. Perception's really good at going from image to, say, next waypoint. And that's actually nicer, because if you wanted to, sort of the contrary point of view of end-to-end learning, image to pixels down to control, you're learning a whole bunch of high-frequency, control is a very high-frequency signal. You're learning a bunch of high-frequency information that you don't really need to learn. So if you went from image to state for your perception module, where state represents like the next waypoint that you'd like to follow, your control is really good at taking care of the rest. So the perspective is use that. And when you train these systems, use the models. Because then maybe you'd be able to like pull out a model and put, if you go from a wheeled robot to a walking robot with a camera, you could really just swap in models. You could probably generalize. These are just things that we're starting to think about now, and I'm really just excited about the conversations I've already had this morning about this, because this is an area where coming into it as a control theorist, as I said, I'm coming from a more model-based perspective, but we're really interested. We know that control doesn't solve the unstructured environment problem, but if we've got guidance from a perception module, control is pretty good. So how do we design that perception module when we know it's in closed loop with control is what we're interested in. So thank you very much, and welcome any questions.